Okay, today is some review of things that you should know, perhaps, if you were paying attention in class earlier, math classes in particular. I want to show you some really neat stuff about complex variables, their series, the fields that they make. Also coordinate systems, which is the next topic here, is the GCC coordinate systems that make Lagrangian, Hamiltonian, Jacobian, all that mechanics possible. So I want to answer a question: what good are complex functions in general, but in particular the exponentials, that make all of this possible? And I've listed here, well, first off, 5 things that have that make complex arithmetic interesting. But then, as far as complex functions and the calculus goes, there are 6, 7, 8, 9, 10 through 16 very different things, but all connected, that make it useful to use complex numbers. You've probably noticed that quantum mechanics just starts off using complex numbers without explaining why. And that part of that explanation should be forthcoming. In any case, as I say, we're going to go very quickly through this, just to review how vector analysis is improved. But in particular, the calculus of vector analysis is the, I think, really interesting part of this. And this is something I wouldn't have discovered if I didn't have access to the Macintosh computer in particular. Now, unfortunately, no links up here for the up-to-date application. We're going to be playing with a Macintosh application. You're welcome in this class to take advantage of some of our loaners if you want to participate in this particular one. But I hope that before too long we'll be having the program called Analyt on the web. And I think it really deserves to be there and take time. In any case, I want to point out also that this lecture comes in 2 parts at least. The part that last time this was given started right here in the vector field potential theory section. If we go fairly quickly through the arithmetic, we can go a little bit further on this today. So I'm hoping to get to this part right here that has to do with what we call analyticity. You've heard that word in high energy physics and things like that. Well, we're going to do the very basic understanding of that. So let me begin by talking about money. The exponential that I'm interested in here is the one that would come if you were to take the old practice of interest, which is often regarded as a very sinful thing, and maybe it is, but in any case, the idea was that only certain people, it was the Jewish people, could loan money and thereby profit. This is in the Renaissance period of Italy that I'm talking about. It was until later the Medicis came on and they realized that they were losing out if they didn't get involved in this. Now, the idea is simple. You give a principal to a bank, and at some time later they pay you the original amount plus some interest rate times the time that they loaned it to you. So I'm taking a very simple example here with 100% interest, just like what I experienced when I spent a year in Brazil, but also Israel has had 100% several times. Things have stabilized in both those countries, I think, for now. But it's interesting just to explore this function and see it in some detail. In this case, it's very simple. With 100% interest, I get $1 and $1 of interest, which is 2. And let's just see what happens if you generalize this. If you fix it so that at the 6-month point, you do the same thing that we just did, but then go on to the full year and do it again, you find that you have applied this 1 plus r times the interest for half a month to some principal that is already gained from being paid off at the 6-month point. And so you get a product of this 1 plus r times t over 2 twice. That's 3 halves, 3 halves, 9/4. That's $2.25. And then if you generalize to a third period, a quarter period, and so forth, a finer and finer periods, you can see here that if I do it at the 4-month period, that is 1/3 of a year, that I earn more than $2 or $2.25, I earn $2.37. And it looks like if I were to continue letting people compound, say, infinitely often, I'm imagining a capitalist there, a greedy capitalist with his cigar and his dollar signs, with a little bow tie that represents infinite interest, what would you get if you did this, you see? And he's thinking, wow, I'd get a lot of money if I could invest at that thing. But the answer is not. As you can see here, where I've gone 1/2, 1/3, 1/4, by 1/4, I'm only picking up an extra 7 cents, unlike the 25 cents I picked up from going from simple to half compound. And what I'd like you to see is how that function varies, and in particular, if it's something that we want to use to calculate this infinite interest function, and you can see the numbers here. Here we got $2.44, and if I go for once a month, I got $2.61 and change, and so forth, 69, 71. Now the ones I've written here in bold-faced green are numbers that are not going to change as I make the period larger. Here's daily. This was weekly that gave it 269, but daily, already 3 digits of that are never going to change. So from here on out, after daily compounding, if I round off, I'm not going to see any improvement to speak of in my thing. I might get 1 more penny out of doing this thing hourly or secondly or every microsecond or every nanosecond. That's what I'd like you to see, is how that behaves, because that is the exponential at work here. So what we're doing here is we're imagining an M compounding function. And here we are for M equal 1,000. Okay, we do 1,000 every interest period. And then 10,000, you see. Then 100,000, then 1,000,000, then 10 million, 100 million, billion even, okay? Finally, by 1 billion, all of the numbers in an ordinary calculator with 9-figure precision are fixed. So you're getting exactly the value of this marvelous constant called E, the exponential constant of Napier and Euler. Euler gets his first letter on this function. So this is the idea of a function that you've studied calculus. They show this, but I wanted to put a monetary swing to it to catch your attention a little better, but also to be aware that it's actually happening in banking right now. In banking now, you can get infinite interest, and they're happy to give it to you. So the idea of saying here, if I rewrite this little mr here, if I write rt over n instead of 1 over m, then I've got a time function here that where you just have rate times time in the exponent. That's what we're going to look at, is that function. That's what's going to make all of the complex variable stuff possible. So this is really an important piece of mathematics. It occurred quite a bit before the Euler theorems and de Moivre's theorems that we're going to show very quickly here. Anyway, this is a terrible way to get the number. I have to multiply it over 100 million times to get this 9-figure precision. It's got to be a better way. And that better way comes from expanding the binomial that defines the exponential. So here's the binomial expansion, the binomial theorem, if you will. And here's the one that we want to apply it to. You see, so remember what a factorial is. 1 factorial 3, 1 times 2 times 3, but also remember that 0 factorial is defined as 1, just like 1 factorial, but all the other numbers are just sequential products of their factors. That is going to be simplified here as we let n go to infinity. If we let n go to infinity, then all of these things here that were complicated, that is the multinomials, become just simple powers. That is, if we can, if we're talking about a really large n, or m, then I can ignore all of the extra terms except for the highest power. And doing that leads us to a series that you know and love, the Taylor series or Maclaurin series for the exponential function. So now you see, as I start to use this, I really only need a small number of arithmetic steps. Roughly here I am getting a precision just with a series of 8 terms. Now there involves some extra multiplication here. We're just multiplying, but here I'm adding and doing some simple multiplications. And already getting 3-figure accuracy. In order to get 3-figure accuracy, I had to do 10,000 products, you see. And here I don't have to do anywhere near that many arithmetic steps. Okay? So, 6-figure precision comes a lot sooner than it does up there. And so forth, as we go to higher numbers. Now, one of the things that I think is important is to see that all functions have a series like that, and that's, of course, part of the calculus to learn about that. But I want to make a connection with the mechanics that we're doing while we're at it. This will be a small amount of mechanics in this particular lecture that I think you ought to see, and that is just the definition of derivatives. So if I take the first derivative of some power series like this and immediately lose the initial constant, then it's only these constants, 1 through n, that I need to define the velocity. And same with the acceleration. This time I'm going to lose this constant right here in that derivative, and then only involve the coefficients with 2, 3, and 4, you see. So these are just the derivation of the Maclaurin series, actually. It's a Taylor series around origin. And of course NASA lets you use funny name, jerk, for the change in acceleration. And then I got funny and said I would be silly like NASA, and I'll call change of jerk inauguration. And I apologized that before because I don't think our president is a jerk, but we may be changing him in for a jerk if Donald Trump makes it through the scenes. So anyway, this is the Maclaurin series for any function for which its derivatives and value are definable at origin, and then it's easy to generalize that to make a series around it. Now, one of the things I want to do before these 2 lectures are over is acquaint you with a generalization of this series for complex numbers. And that series allows you to not just use positive powers, but to also have a small number usually, but it's possible to have an infinite number of negative powers as well. So we'll be doing some more with this as we consider complex functions and numbers. But that won't come today. That's very much the end of this 2-lecture series. In any case, I want to remind you that mechanics is right here as far as sophomore physics goes, pretty much. The good old University Physics 1 formula for position is your initial position plus your initial velocity times time plus 1/2 over 2 factorial, which is 1/2, the acceleration if it's constant. And in other words, if you maintain that constant. But the idea is that any function, however wiggly, as long as it isn't discontinuous in any of its values or derivatives, could be defined for all time by extending this. That's a little bit unnerving. The idea is that all the information about a function for its whole expanse is contained, and if you take a microscope and look very closely at some point that you call origin. It's, you know, just that's a little bit of a squeeze for your brain to think of that, you say. And so with a microscope you can predict the future. Well, nobody's been able to do it yet, but you can certainly think about it, and you can write equations like this that look like that's what's going on. And also setting all of these initial values equal to 1. And this would be true for any point on the exponential. That will give you, in this case, if we're talking about the actual time equals 0, the exponential series that we were talking about before. Okay, so these are some of the wonderful mathematical things that you often or brush over in a course. And one of the things I would make sure you see is the geometry of this relation in particular, but also I'd like you to see it for the sine and the cosine functions, which you know, do nice wheels. And the idea is that you're going to take the exponential function x of t equal e to the t, which is the red curve here, and you're going to approximate that curve by first 1, so that point is on the curve, but also 1 plus t, okay, 1 plus a line. There's the first approximation that will carry you a little bit outside of that point, you see, before it deviates from the curve, plus a parabola. That's the next thing in this series, you see. The quadratic parabola, you see. Well, it approximates a little bit more of the exponent before it peels off from the red curve. And the next one is a cubic. The little green thing there, it peels off to 1 pixel, right about in here. Okay, and so forth. They all kind of end up kissing the exponential for a while and then peeling away. And that's what I'd like you to see. And the same thing is true on the other side, on the downside of the independent variable t. Here's cosine and the sine. Now I'm skipping over the derivation of their Taylor series, but I'm going to assume that you've seen that, but you may not have seen how well each of these terms does at approximating, say, the cosine. Now the cosine is an even function. It has a symmetry around the origin. So I am only going to be using the even, that is the symmetric polynomials around the origin, even powers of the independent variable t. But that means the 0th power, which is just the 1 that starts the cosine at origin. But then the parabola, you see, is not a bad approximation, at least to 1 pixel, until about there or so. And it's definitely gone south, so to speak. And the same is true for the 4th power being added to that. The 4th power is this curve right here, and you see it does a nice job with its coefficient, of course, 1/2, of approximating the curve out to about there, you see. So the parabola came off about there. The quartic is coming off by 1 pixel about there, okay? And so forth. The 6th power comes off about there. It's always about the same distance between each order of the series. And this goes on and on and on forever. The distances between the peel-off points, that you have to define them by what precision do you like at the moment. And if you're a computer graphics jock, you're going to want it within a pixel. If it's within a pixel, there's nothing to see from the difference between, say, this approximation here to 12, or this approximation here to 8, which is what's been written here. It will stick to the curve as far as you can see. But of course it isn't. Inside there with a microscope you can see that the 8 is only right exactly there. So this is a little bit of lore of these series. This is what it makes it very unlikely that power perturbation series can close out something that oscillates a lot. You hate having to get just another one and then another one forever. And it doesn't improve for the odd functions, which is the sine. So that's something I think is worth finding. And again, something I wouldn't have done by hand. We're very thankful for the silicon on this one. It makes it very easy. Just a few hours work at the most to get on this. Now,
have you done it the other way around? Have you looked at representing a parabola or a
using Fourier analysis? You bet. And that's fun too, and we're going to do that later in Unit 4. It's really quite amazing, and of course you're probably familiar with the Gibbs phenomena, which makes it really tough on the functions that have bends in them, infinities of slope.
I think that a lot of people have already done constant functions using cosines or something like that, where you see the Gibbs phenomena.
Yes.
But I don't think it is as common an exercise to see people trying to represent a parabola or a cubic graph or something.
Well, the thing we're interested in is taking various functions that are defined by groups and making them work, you see. And since those group transformations are themselves exponentials, and something I didn't mention, thank you for the question, is that we're going to be generalizing this whole business to spinors so that we can do things in 3, actually 4 dimensions. Can't do everything that we could in 2, but we can do a lot. And that'll be in Unit 4 as well. Okay. Here is something that really freaked people out, I can imagine, in the 1500s or 1600s. And well, I would say in 1600s you were supposed to know this if you were a mathematician. And that is that if you take the banker's interest rate and make it an imaginary number, okay? And we unfortunately have, during the savings and loan collapse, but I think also in the major collapse of 2008, a lot of people that were doing imaginary something or other with their banking, okay? And what's really funny about this is if I put an I there, I get my accounts not to grow like they're supposed to, but to just wiggle, okay? And this breaks up into an even wiggler and an odd wiggler. That is, it breaks up into a cosine and then I times the sine. And that's our Euler theorem that is so important for getting complex numbers off the starting block, so to speak. So this Euler theorem is going to be behind just about everything we do, and the generalizations of it, where we have spinor operators, is also important because it will have actually 4 numbers here, not just 2. But real and imaginary is enough to get us started with some interesting mechanics and field theory and all of that kind of stuff. So this is a part of the lecture that I wanted you to see. It's very elementary, but then it doesn't hurt to review elementary things, looking at them from another point of view. particularly a geometrical one. And the thing that I want to emphasize from the start, that the answer is, why do you use complex numbers in quantum theory? Well, quantum theory is about incredible wiggliness. Everything in quantum theory is waves vibrating at different points in space and time. And we use clocks to represent the phase space of those oscillators. And that's where I would say that's the major reason for having the complex numbers helping us, having our wave functions have two components, a real and an imaginary part. And basically, where is the functions and where is it going, how fast is it going, is indicated by the imagination precedes reality by a quarter of a circle, is the way I like to say that, and make fun of the way businessmen now have restricted our scientific efforts. They have to get everything by a quarter so they can satisfy stockholders, right? Anyway, the cosine and sine that are part of that complex number are visualized, and most of the time, as you'll see, we're going to be having time functions with a minus sign here, because if you're up here with a positive velocity, you've got to be going that way. You've got to be going toward higher values. So our phasors of normal mechanics rotate with a clockwise sense. Of course, anti-things are the opposite, but let's not get into that just yet. Okay, now, oscillator phase analysis, this is the thing that I would answer first if you ask me what good are complex exponentials. And I would say complex numbers provide automatic trigonometry. So if you can't remember in an exam or something that has a closed book and you aren't allowed to do anything but think, what is cosine A plus B and sine A plus B? And believe me, as you get older, it's harder to remember things like that. So all you have to do is factor e to the I A plus B into e to the I A times e to the I B. Once you've done that, you say, then you can just rewrite the exponentials in Cartesian form or vice versa in exponential form. So what I've got here is e to the I A plus B. I haven't factored it yet. So I have a cosine A plus B, which I've indicated in green, and a sine of A plus B that goes with the imaginary part that I indicate that way, and in red. And you can see here that I have a cosine of A plus I sine of A as the expansion of the single factors of the exponential. We're going to play this game over again with spinors, except then they won't commute. But here they do. Doesn't matter. I would then get product of this and this, it's this, and then I squared, which is a minus, and the product of those two, I'm done. I've got my cosine of A plus B, and there's the trig identity, okay? So it's things like this that can save you if you're having some trouble on an exam with some trigonometry, and there's lots of other things that do this. Vector sums, cosine rules, all this kind of stuff is all easily available de novo on a blank sheet of paper. You can quickly rederive the cosine law or the sine law or a bunch of other things that are much easier, okay? And then, as I've said already, when we talk about phasor clock with a minus sign, that's a real phase space. It's just that we've scaled the oscillator phase space. So this is the velocity divided by omega, so that you get a circle and not an ellipse. If you have a high omega, this would be an ellipse. If you had a low omega, it'd be an ellipse this way. You'd like to have a circle, and that makes the arithmetic easier. So there are, you can look at a complex number as its real and imaginary part, that's called the Cartesian components, or you can look at it in polar components, that is, its polar angles, its radius, which is called the amplitude or modulus, and the argument, or phase angle, which is the angle theta, in this case the minus omega t. Okay, so it's just stuff we're going to work with. And remember, always have these conversion things. This is basically what the polar coordinate to Cartesian conversion device on all of the mathematical calculators is doing this conversion. That's what it's for. But whenever you have to convert, you use an arctangent, but the arctangent, this is a failable thing, this is multi-value. Instead you use a tan 2. I've mentioned this already, it's worth mentioning again, that you then put in two values, y and x separately, and then you won't get in any trouble with what quadrant are you in for your angle theta. Okay, now this I also want to point out when it comes to talking about vectors and rotations. The effect of an e to the I phi, that's a typical complex number, but let's make it a complex number whose modulus is 1. Operating on a general complex number that has any modulus or angle is the effect that you see right here. That is, I have a real part, it's the cosine times x. There it is. And then I have more of that from these two products right here. There's a minus sign on it. Now it's y and sine. And then the imaginary part has its part. Well, the way you'd write this out if you were doing this with vector components and vector analysis is with a matrix that looks like this. And how do you see that? Well, you just rewrite this thing with a unit vector x, which is silent in the complex analysis. And that's another advantage of the complex analysis, is that you don't put anything in front of the real part. You put an I in front of the imaginary part. The I is equivalent to a unit vector in the y direction. So we're going to play a game from now on when we deal with vectors, is we're going to see the vector in the way that you would do it by Josiah Willard Gibbs notation, and then the way you do it with complex notation. And you see that and quaternion notation were all available at the end of the 1800s in math courses in Europe. And Gibbs brought back only a fraction of that mathematics, which led to the Gibbs notation. Usually you put an I here and a J there, right? Well, those are the first two of Hamilton's quaternions, I, J, and K. And he brought the K home as well. And that's vector analysis, okay, the notation that we owe to Josiah Willard Gibbs. They call it, sometimes I say, this is the emasculation of the spinor operators. We'll talk more about that later. In any case, this is the matrix relation. There's that, there's that. Okay? So, and that's what happens geometrically. You apply this thing, and it takes any vector and rotates it by phi. And you can see that easily with this notation, you'll see. A little more complicated for 3 dimensions, but we'll get to that. Okay, I want to make sure I have one other thing that's necessary. Complex products provide two things. When you do a complex product, you get two things out of it, because it's two-dimensional. You first of all get the dot product, and then you get a peculiar one-dimensional cross product. Okay? How does that happen? Well, let's take two complex numbers and do their star product. Now, what is a star product? A star product is where the first factor is complex conjugated. So I write that. That just means turn all of the EY's down. Turn all of the I's down. Turn all of the I's anywhere in there negative. That's all you do. And it's understood that these components are real, just like they would be in an ordinary vector analysis. Okay? So when I put this thing together, and we're going to do this trick several times before we're done with these 2 lectures. I put these guys together as a real part and an imaginary part. And you recognize this one immediately as the dot product in 2 dimensions. But this is the cross product in 2 dimensions. You don't usually think of cross product in 2 dimensions unless you imagine a Z, a big capital Z that's perpendicular to the plane of the paper or the screen here. And really should have bars around it because this is just a number. But that's what we mean. Sometimes we'll leave all of that stuff off while we're doing our 2-dimensional stuff, but it's important to remember that's what we're dealing with here. Okay? So this imaginary part vector, cross product, but it's just the Z component normal to our XY plane. Dot product is just a 2-dimensional dot product. This is sort of new to most people that haven't looked at complex numbers in this way. But it's also a neat way to get various identities, like the cosine and sine sum or difference. Okay? Because if I take the dot product in polar form, you can see right away what's happening. I'm getting d minus a angle. And then the magnitude of these vectors, which is the square root of the sum of their squares, is the radius, the magnitude of each of them being product. And I get a cosine and a sine, as I should. One of them being cross product, the other dot product. Okay? And you can take that thing into Cartesian form and see that it's xy minus yx. That's showing up there in that cross product. Okay? All right. Now, derivatives. This is where it gets a little bit squirrely. But by twisting it a little bit, we get something that's really quite powerful. A complex derivative, that's a dz, this kind of thing, or maybe this kind of thing. We have to be clear about that. A complex derivative contains, in its real part, the divergence, and in its imaginary part, the curl. Now we're talking about a whole vector field. And that's what we're going to talk about for most of the rest of today's and part of Thursday's lecture. But here's the thing you have to do. You have to sort of work the chain rule. We have two variables here, x and y, or z and z star. They're independent variables. You're used to these being independent variables, but it's a little hard to stretch your mind is to imagine that z and z star are independent. But they are, because there is a one-to-one and onto a transformation between them. This is it right here. Okay? It's kind of what we showed before, the Cartesian to polar. But the idea is that a derivative with respect to z is going to have 2 parts if you think of the independent variables x and y. So what I need is I need to know what is the Jacobian of the transformation in 2 dimensions. That is the partial of x with respect to z, the partial of y with respect. All right, we're coming back on the day after a squirrel blacked out the university power system. And this is where we were, but I've switched over to lecture 14, and this is a review of lecture 13 as you would do if you had gone that route. But we were just discussing the differential properties, the complex derivative properties, and I want to show about its real and imaginary parts, which are vector derivatives that you're familiar with from vector analysis. And this is an easy way to understand and get them in some interesting situations. So we already have z, and then the complex conjugate of z, which is taking the I and changing it sign. Those are 2 independent variables that probably aren't familiar with as, at least as familiar as the x and the y coordinates. That's much more comfortable sort of independence. But the z and z star one is just as important. And what we're doing here is we're talking about a derivative of a function with respect to just one of them, the z, and then also of interest is with respect to z star. So we have here the chain rule. I put these two sort of chain saw rules, what I call it. You hack this thing in half and slide one of them one way. In this case, the f goes over here and the z goes over here. And I stick in one of the independent variables for the Cartesian and the other one, y, there. And then we know these coefficients, they're Jacobian coefficients, if we just simply take the derivative of x with respect to z and y with respect to z, that's this and this, you get a 1/2 for the x. That is the partial derivative of x now has a coefficient partial x with respect to z, and that's 1/2. And the next one, the partial y with respect to 1/2, it has a 1/2 but with the I in the denominator, so that's a minus I half. Now you should notice that z has a plus sign, but the operator that is the ddz, that is the z in the differential denominator, has a minus sign there. So remember that, because we're going to make use of both of these, but principally that one. Okay, so that's the idea for calculating derivative of our field function, our complex field function. The force field F has x and y components that we're going to be playing with here over a whole coordinate system x and y. And the derivative of that with respect to z is what we just said it was, this minus I partial f with respect to y following partial fx. So we do this usual thing, we put these together into real and imaginary parts. Okay, there's a real part here, then there's a minus I times plus I, that's plus 1, partial fy with respect to y. Okay, recognize fx x and fyy as a divergence of two-dimensional thing with the 1/2. We're going to talk about that 1/2 a little bit in just a minute. And then this one right here, the imaginary part that we get from pulling out everything that has an I in front of it after you do the product, is this one. And that is a single component of a curl of that vector function f. Now I put all the notation that goes with this funny way to indicate a curl of one component, and that is that we imagine that capital Z as the vector coming out of the screen perpendicular to the plane that has the variables we're actually working with. So this curl that you're used to is the right-hand rule, x into y, say. The idea would be that this would be a big Z. So we do all our work in the plane, but we imagine that there's a line perpendicular to it that can make us happy about the curl, that weird kind of one-dimensional curl. But anyway, it's the imaginary component. That's the idea. Complex derivative contains a real part of divergence and an imaginary part of curl, so we're going to work with that. Now, what I'd like to talk about is that when we have a field that is a function of, say we had a field that was a function of z star, then this derivative would be 0. So basically what we can do is take any analytic function, and that's really what an analytic function was. We'll explain this a little bit more later on. But the idea is that a function that is just a function of z would have a 0 z star derivative. Or if I took the f and it was only a function of z and conjugated it, that is, made it into an f star, then it would be a function of z star, and it would have a 0 derivative with respect to z. So this conjugation, this changing I to minus I, is a very powerful sort of argumentative source for arguing about things. And I would say that you name for me any of your favorite functions, z squared, z cubed, sine of z, arc sine of z, and so forth. Logarithm of z is what we're going to see fairly shortly. You name functions that you've worked with over time, and you will produce a vector field that has no divergence and no curl. And that's a very important sort of field. That is, it's a field that satisfies Laplace's equation. We'll prove that. Okay? You also produce a weird coordinate system. Just name your function, and there's going to be a coordinate system that goes with it that most likely will be interesting and useful in many cases anyway. So that's what we're going to spend a lot of time talking about, is the fields and the coordinate systems that go with them. Okay? So, the example that I'm going to take first, and you would think this would be not a very interesting one, but I'm going to take a field that is just simply z. Well, a constant times z. Let's allow for a complex constant, but we'll make it real here, just to keep the arithmetic simple. And then what I'm really going to be asking you to plot is not x plus iy. I'm going to be asking you to plot z star, which is x minus iy. And definitely not a function of z, so it has a 0 z derivative. Okay? So this field here, which I call f with a little star written up as a superscript, the actual fx's and fy are real, so it doesn't mean you take the complex conjugate of them. You're just labeling them as this weird field that's been conjugated. Another label that I'll use is just big F that we use in physics for a force field. And then what we're going to get for that force field is no divergence and no curl. And I'm shortening up this notation a little bit here. Okay, so here's the divergence. Let's check that this works. Partial derivative of fx is x right there. I'm going to take the x derivative, and I'm going to add to it the y derivative of the y component, which has a minus. Well, you can see what happens there. It comes out to be a minus a. Nada. And the same thing with this one, except this one is really 0. This is the partial derivative of the y component with respect to x, and the y component was had a y but no x, so that identically 0, and then the x component had an x but not a y, so that's identically 0. So that's out. Okay? So what we have whenever we pick a function of z, something we've worked with in calculus, some function of x, but I'm going to put in a complex z, that function can then be conjugated, and it will have no z derivative. And the field that has no divergence and no curl has a name. It's called divergence-free laminar. Laminar means that it's curl-free. Okay? So we're going to see a whole bunch of fields that have that property, and they're, of course, interesting for physics, all kinds of physics. We'll mention that as we go. Anyway, this is a picture of that field that you get. So once again, this, you know, what good are complex exponentials and all of that kind of stuff? Number 7 is really a cool one. Invent source-free vector fields and coordinate systems. We'll see where the coordinate system comes in just a minute here. Has to do with potentials. Okay, so far so good? That's just a summary of what we just did. But here's a picture of it, and that's something we can make fairly easily using this program called Analyte. And you can make a Mathematica and other programs do this sort of thing. But this particular program is set up for this discussion, so it does make it important. And what I'd like to show you first is the control panel, which will be something like what we'll have when we get this on the web. But I'm going to have a menu of functions, and I would draw your attention to the center column here. we were just looking at a function of z equal a constant times z. We're going to look at some of the others in a minute. It might be helpful just to begin with this, to look at a function that has simply a constant as its thing. And this is the one that's chosen here, and you can see the result over here. Now, the constant a is being set up here. This is a equal real number 1 plus I times 1.25. Let's get rid of that component right there and make it the imaginary part of the constant 0. So this is a real constant, just like we're going to mostly work with today on these functions. And go ahead and plot the field that you get. And what you get is a bunch of arrows that have no y component, but an x component of 1 unit. So there's a uniform electric field, kind of thing you see in a parallel plate capacitor, if it was electric. Okay? So that's a good one to start with. But what I'd like to show, of course, is the one that is right here. So I'm going to go ahead and just simply click that choice, f of z, force field equal to just z to the first power. And so I'm going to set this up and then just draw. And that's a non-trivial vector field. Okay? This is just f of z equals z. Okay? That's cool. All right? Now, it's a good one to work with because it's so simple. But you can see if we're talking about fluid flow, and that's one of the physics that we're doing here, is what Feynman calls dry hydrodynamics. If you're talking about a flow of incompressible fluid with no vortices or anything, that's a divergence-free laminar field. Now, you know, this is a good chance to learn what does the divergence measure, and also what does the curl measure. This thing at first might say you've got, looks like I've got some curl here, don't I? Because I've got a big vector here and then a lesser one here. Turns out the curl is 0, identically everywhere here. And the same thing with the divergence. You see arrows diverging, but the divergence is in fact 0. Now, one of the things I would point out to you is that if I had not done that starring of the function f of z equals z, that thing where I turned the y component to negative, which is what I've done here, then what I would have is a very divergence field. Because just imagine each one of these arrows turned up by the same angle. You see, this one would be up, pointing away from the origin. This one up here would be way up, pointing away from the origin. Every one of these arrows would be pointing away from the origin and getting bigger as you go out. That is a sign of huge divergence, actually constant divergence. Okay? Everywhere. So that little starring we do is the trick. That's what gives us the fields that we want to talk about. Analytic field. Okay? At the very end of this lecture, I'll try to bring up how you can extend this to non-analytic functions. That is, functions of both z and z star. That's one of those things I explored a little bit, but it's something that it might be worth looking at that in some more detail. But in any case, here is a very nice example of a laminar DFL field. Okay? Now you can see what it really amounts to. Somewhere there's got to be some divergence. The divergence for this thing is an infinity. Way up there, or way down there, or way over there, or way over there, you see. The divergence coming up here is positive. That'd be north and south, and I guess you'd call that east and west. That one is where the sink is, you see. We'll explain that more later on, too. there's a geometry of that that's really beautiful. It gives you a global topology of these functions to work with and think about. So there's a good deal of geometry here. Now, where the coordinate systems come in is when you look at the potential that goes with this force field. And this is where we use the mathematician's convention. No minus sign on our gradients and nothing funny on the curl either, but then you didn't know what sign to use there anyway, so whatever we get here will be acceptable. So the idea is that if you have one of these fields, these DFL fields, and I claim you can get one from any function of z by starring, it has to be a gradient of a scalar potential field. You kind of have heard this thing. But it also, the same field is a curl of a vector potential. And this is cool. This is something that, you know, is not explained very well in any of the mathematical physics books I can see, and certainly not in electromagnetism. So there is a complex potential. The real part will be a scalar. We'll call it uppercase phi. And then A, the usual notation for that, is A, for amplitude actually in electromagnetism, but we're getting ahead of ourselves there. And this exists. These things, this complex potential exists for any function that you think of. And the idea is that that function, f of z, should be the derivative of this phi that we're looking for, this phi right here. The little lowercase phi is a complex function, also an analytic function, as we'll see later. And its complex conjugate, which just puts a minus on this because these things are assumed real here, or will be in our particular case, has a z star derivative like that, giving this field. That's what's going to happen here. So let's see, and this is really the cool part, is to get phi of z, we just integrate it as though it was an ordinary calculus function. Okay? And then you isolate the real and imaginary parts. Okay? So what you do is you take our phi, our f, you take our f, this is force times incremental distance, our az, okay, dot dz, there's your complex potential right there. Now you really want the star of it, but this time it doesn't matter that much, because the two separate things, you can specify what sign you want to use for that guy, more or less arbitrarily in most of these cases. So what we're talking about here is 1/2 az squared, that's x plus iy squared, quantity squared, and that has a real part of x squared minus y squared, and an imaginary part of the product of x and y times 2. Okay, but we have a 1/2 here, so I just get the constant times xy here, and I get a half of x squared minus y squared there. Okay? All right, so that's what those things. Now the question is, what do these things look like, and what do they do on our graph, you see? This is the picture that I would like to show in detail up there, but it's step by step. Let's take the scalar potential first. Okay? And so let's swivel over to where the computer is making this graph, and look at the control panel first. And what I have checked here at the very top underneath the plot, the force field, is that I only want to plot individual scalar potential lines, that is phi, and I'm talking about uppercase phi, which is not shown there, but that's what I mean here. And we've got it clicked so that when I draw that curve and then put the cursor somewhere and click it, I should get a constant field. Now, the phi is written in numbers up there, and you can see the idea is that as I move along that line, I'm keeping the potential of 1/2 volt, if this were an electrostatic problem. So this is a 1/2 volt line, constant, equipotential. contour, if you will. And next to it are other contours, you see. Everywhere I click, I get hyperbolas that have a constant potential. In this case, the potential is up to 4 volts. Okay? So I'm rising here in the potential, a mathematician's potential. There's no minus sign on this one. Okay? Now, obviously, there's going to be crossing an asymptote somewhere in here, maybe right about there, you see, and it's very, very hard, you see, to get right on that thing. That's pretty close right there. And then I'm just arbitrarily picking the ones here, and you can see I'm going into the negative region here with that potential just above the arrow there. It's being written. I'm already minus 2.7 volts. And then I come back over here, and I'll make some more hyperbolas with positive voltage, and so I'm climbing up as I go toward the direction of the arrows. And remember, the force is well, not with the minus, not the physicist minus for this. And then down here, it's also downhill as I go to the lower part of this figure. Now, all of these curves are being memorized by the computer, so they're stored. And I can go back to the control panel and ask for various things. This time I'm going to ask for the ability to draw a vector potential constants. Or I can do both at once to save time, but let's just do one at a time here to get a feeling for this. And this is where the coordinate system comes in. What we're going to do anytime I click here is get a blue line, which is a streamline, kind of like a water flowing. Okay? These are all lines that go tangent to each vector that is next to that point on that line. And they're hyperbolas too, it's just that they're equilateral hyperbolas. Okay? So that's what we're building here. Constant streaming potential. Now that's a hydrodynamic phenomenon or magnetostatic phenomena that most people aren't familiar with. But a vector potential is just as useful as a scalar one for visualizing the physics of things like this. So it's worth noting. I'm going to go ahead and put a few of them down here just to fair this thing out. Well, one of the things you should notice is I've been more or less keeping the intervals between them constant, just so it looks like a coordinate system, is this is our coordinate system that we get. This is a GCC, of course. Any curved linear coordinate system is a GCC. But this is also, and we have to prove that, this is also an OCC, a subset of all the GCC. Everywhere a streamline crosses an equipotential, you've got to be perpendicular, because the gradient of the red voltage potential line there, the gradient has to be normal. In this case, a positive normal. We're using the mathematician's definition of gradient equal force here. So that makes a right angle between the streamlines, which are tangent, you see, to the A equipotential, the vector streaming equipotential. So this exposes the geometry of the function f of z equals z. The simplest function that's not trivial, f equal constant we looked at, and that would just make a Cartesian coordinate system. This is the next thing up. Kind of neat, right? Okay. Now, a couple of things that need to be said for it. When we draw these pictures, I like to put the information there. There's the field, actually, the one that we're plotting. F star, Z star, Z star. That's x minus I, y. There's the actual F. It's just extracted from there. There's the potential that we just calculated, and it's got two parts, a scalar and a vector. And the question is, which do you want to use? And the answer is either or both. I can take half and half, or I could get rid of this one entirely. Then I've got to take all of this one, which would be 2axy. Or I can kill this one, just ignore it, but I take away the 1/2 then. You see, I get to do this because they give the same result, and that's something we need to make a point of. Now here are the queered coordinates of this system. If I were to carefully draw it so these things really did mimic constants that went 1, 2, 3, 4, or 0.1, 0.2, 0.3, however fine you want to make it, and the same for the A. Okay, so these are our coordinates equal a constant as I would normally define it. And this is one of the coordinate systems that we're going to use in classical mechanics for some things. It's just being given to us for free. You see, we derive it essentially for free. And that's what's nice about computers, it makes it free, right? I don't have to do an enormous amount of plotting to come up with this. Okay, so let's do some more with this field potential. And I also have just stated what I call the half and half results. Now, these half and half results have a very famous name. It's called the Riemann-Cauchy derivative relations. We'll get to that very shortly here. So here's the deal. What I want to show is actually this thing coming to us in a very direct manner. I want to actually see the individual terms here. So let's go over this way again. We're taking a derivative of a phi star with respect to z star. Okay, and remember that that derivative with respect to z star is the one that has plus in it. And this phi here that we're talking about, this phi star, phi itself had a phi plus IA, but phi star has a minus. Now we do worry about the signs, okay? But really all that has to happen here to keep these two things within a plus or minus sign of each other is have a plus here, a minus here like we do, or we can flip it. Those are conventions that might come useful later on. But anyway, this was probably the one we'll use throughout. Here I separate out, you see, the real part, okay? So I get a vector here. There's the x part, there's the y part, right? That's what I is a unit vector, okay? That indicate that that's a separate entity, the second component. And the same thing with this thing. The thing that involves A, I've got a x component, and then I got a minus sign on the y derivative of A, okay? Now what you should look at, and this is again, should have some extra notation on it because we're talking about, curl in x and y plane. This is the curl of the vector A. That's what you've got here, partial A with respect to y minus partial A with respect to, and I'm just realizing I've got that backwards. Here's the x. Okay, this is the y component. That's a typo I've got to get rid of. I've had 2 chances to fix that and I haven't done it yet. But there's the right answer, and this has an x on it. Okay, so there's the curl, divergence, it's x and y in order. Okay? Now, we are using this definition. Okay, this replaces the thing that we talked about before. But here's the half and half result where you really see what's involved. In either of these cases, the gradient, okay, which I take the partial with respect to the phi, that's the phi right there, then there, okay, that's the gradient. Doing a partial with respect to x kills the y term. Here it kills the x term, okay. End up with ax and minus ay. That's the force that we are plotting when we plot those green vectors on the screen. And then here, the same thing. I do a curl. Now I've got the x in the right place, and I get the same thing, okay? That's the half and half idea. So I can take any combination of these two If I'm talking about analytic functions, I can get away with it. It's when you have non-analytic functions, you can't do that. Then you really have separate entities. And you will have a GCC coordinate system when you do that. It won't be OCC like these nice things. But anyway, this is where I should use the mathematical terminology to describe what we mean by half and half. These results are called the Riemann-Cauchy relations. Basically, one of them is the partial phi with respect to x is equal to the partial with respect to y of a. Okay? That is, in any analytic function, the partial derivative of the real with respect to x has to be equal to the partial derivative of the imaginary with respect to y. Imaginary part of the function. Right? And then the other side of it is the y derivative. This thing right here has got to be negative the a derivative with respect to x. So, same deal. This is y and this is x now. This is x and y here. But with respect to the real and imaginary, I have a minus sign. Those are the Riemann-Cauchy relations. Very important. The test of analyticity that most textbooks were saying. But there's a simpler test for the things that we're doing. And this is where you really have to think about functionality. But once you've done it, it's obvious. So, what's analytic and what's not? And most people think of something being non-analytic, well, it must have gone to infinity or done something terrible. Not true. It's functionality of the simple kind that we're talking about here. Now let's go through just really quickly here. I'm going to let you read this through, but you can see what I'm doing. I'm just reviewing all of the mathematics that we've done so far with the derivative with respect to z and with respect to z star. See what it gives. Okay? But the criteria for field function to be an analytic function of z is the derivative with respect to z star is 0. That's what we've been playing with here. In other words, the function must not be a function of z star. Okay? This implies that f of z satisfies the differential equations known as, and that's what's coming out of here, Riemann-Cauchy. Okay? But you could play a different game, and I don't see this played very often, but you haven't really got a situation where I need to play it very often. But you can have a field function that is an analytic function of z star, right? And you'll get anti-Riemann-Cauchy conditions for that. You see they're different. Now the minus sign appears here instead of here. This one's got a plus sign, right? So that's always available. There's always a flip to any of these sort of things that we make a duality, okay? But let's get really down to brass tacks. What's analytic or what's not? For example, if I had a field like this, 2x plus iy, okay? A field that had a component 2x and a minus y. Okay, is that an analytic function? See, is that what I want? Let's just talk about this one with the plus sign. Is that an analytic function? See, well, you try it out, okay? Remember, z equal x plus iy, and z equal star is x minus iy. X is the sum of those two, y is the sum. So substitute the x in here and the y in there and test it. Okay? Stick in this where x is. Stick in this where the y is. 4y now becomes 4 times that mess. Okay? Sum them up. Okay, z plus z star here. 2z minus z star there. Okay? That's 3z minus z star. You're out of business. This is not analytic. And it's not infinite or anything, right? Unless you let the z go to infinity, right? Okay? So that is what we mean by analytic, okay? Not being analytic is it's a function of both, okay? Now, it still makes it an interesting field, but it's a field where you need both the streaming and the scalar things. One of them isn't replaceable by the other. They're dependent. Okay? Another example. This is a famous one. We're always talking about probability in quantum mechanics. That's the sum of the real squared plus the imaginary squared, x squared plus y squared. Is that an analytic function? Boy, what a nice function that is. Well, obviously not. It's z star z. It's a function of z star, as well as z. It's not an analytic function of either. Just like this. Okay? What about this little guy? X squared minus y squared? Well, we've already seen this one. We know the answer to this one. You plug that one in and you just get an analytic function, z squared. Okay? So this is something that is just not clarified, certainly in the physics literature that uses complex variables. But I hope you won't forget it. Okay? Now, here's where it really gets fun, is to look at the circulation and flux. One's the imaginary part, the other's the real part, which, and so forth. And then the curvilinear coordinates, once again, what are their Jacobians and all that. And I've given some problems on this to help you remember it. Okay? Now, if you have a complex potential, and you measured at one point, and then you measure at another point, say an initial point, and then later on, and you imagine that you can get that, of course, by an integral of fz between z and z1, then this integral can be replaced by just the differences in potential. And I mean complex potential, but we remember you can just use the real part if you want to. But it's also interesting to look at what this one measures. You see, this one you know as a line integral being measured, right? Well, that one's a flux integral. You're getting both for the price of one. Okay, this is definitely a day for twofers. Two for the price of one. Okay? So here is a summary of that. But look at what you have to go through to make it work. We're interested in an integral of f of z dz, but I can take the star of and f stars. So we're interested really because we had to do that trick of putting the star function in for the one we're actually going to do physics with. Okay? So I'm going to be talking here about the complex conjugate of that function, which will have a minus sign. Meanwhile, dz is just dx plus I dy. That's not so fancy. But now I put them together. Okay? There's a real part. fx dx, and then a minus I plus I, that's plus fy dy. Okay, that one you can really identify as the line integral of the work, force times distance. That's very comfortable. This is a little weird. Fx dy minus fy dx. Well, that's the force vector cross dr, but dr dot, that magic vector big Z that sticks out of the screen. Okay? This is a triple product. You know how to do that. Change it around, so f dot dr cross ez, and then notice that the dr cross dz is what we would call a well, maybe a surface differential. So what I'm looking at here is an integral of how much f vector crossed the border. Here I'm looking at how much is along the border. F dot dr here, F dot ds, ds being that here. So this imaginary part of the integral is counting crossings, that is flux, through an arc of some kind, but you think of it as a surface of unit height that you count flux going through. Okay, so this is one that a little hard to get used to, but this one you already know. This is just circulation. Okay, so circulation and flux. Now the circulation, the thing that you used to associate with curl, which is the imaginary thing, now it's the real part, and here the thing that involves something you might think would be the real part, but it's not. It's the imaginary part of this image. Okay, so that completes our discussion of the marriage of the analytical function theory to what's really sophomore physics or junior level. I mean, you know, when you work with electromagnetism, you see. But it's also, and this is what's really interesting, is in these diagrams here, I could be plotting a geometry of a soap film. In other words, I make some kind of weird wire and I dip it in a really good detergent solution. I pull it out and there'll be a surface with all kinds of curvature you see on that. That's what this is right here. If we plot the real and the imaginary parts of the potential in 3D, which is what we're going to do. Okay? And this is where it's going to be challenging for getting on the web, because then we have to use WebGL and all kinds of weird things to make a nice job of it. When we get done, I think it'll be really cool. This is a picture of our function right now. Now I've done it in 3D, and that's the way I would have you look at these things. We'll spend some time with this so you can get a little practice. But this program allows you to draw this thing in such a way that you can look at it either wall-eyed. That means that you take your right eye and somehow get it apart so it's looking at this image, and your left eye looks at this image. That is what most stereographic viewers do. So if you have one of those 3D viewers, you can stick those pictures in the textbook into them, and you'll get an image without having much practice. But in order to view it from where you're sitting in an audience on a screen that's up there, we have to draw this thing flipped, and that's called cross-eyed. That's where you cross your eye so that this eye looks at this and this eye looks at that. And when you do that, you bring them together into one image in the center, and you see 3D. Now you can do cross-eye or wall-eye of any of those things, but when you do it, you'll see the whole thing turned over. Let's give it a few little tries here. Now what's going to happen here is that the streamlines and the equipotential lines have been memorized. So every time we redraw this in some weird way, all of those curves will be shown in the right place. And let's go ahead and stop this thing, and without choosing a new function or anything fancy, I'm going to go for cross-eye 3D on that. But just for the heck of it, let's go with a mono picture just to see what it looks like. And what I want to do is I want to plot the scalar potential uppercase phi. Okay? There it is. Okay? Now, you don't really need 3D with this one, and it certainly if you can rotate it like I'm doing, you can see that it's a saddle. And that would be an interesting soap film if I had a wire with no sharp points on it that was just the border of this, and I dipped it in detergent and pulled it out. I would have a glistening, sort of iridescent film that followed the lines there, the surface that you see there. Okay, now, when you
Can you explain the physical reason why the soap? Is it just a minimization of energy thing?
Well, something we haven't mentioned yet, but the Riemann-Cauchy relations will turn out to make either the phi or the a function of x and y a solution to Laplace equation, which is divergent gradient, that's del dot del, okay, of either one of them to be absolutely zero. So basically what you're saying is the curvature the average curvature, that's what you're adding up, 2 second derivatives, right, in x and y, is 0. So everywhere on this surface, if I have curvature this way in the x direction, I have to have just as much in the other direction to cancel it. That's equivalent to finding the minimum energy, if we can believe a scalar stretch sort of thing, for the silk film.
Okay, then follow-up question, does it change if you add gravitational effects?
Oh, you bet. You bet. I mean, it will sag just a little bit.
That's what I was thinking.
Yeah.
Sure.
Yes.
The plus has
I mean, of course,
Start with a perfect circle, right? And if the soap film had enough heft to it, how would you get that? Maybe you could use, instead of water, you'd use tritium or something. That wouldn't do it.
But if you
you'd
just
need
put
more than 3 times.
If you just put more detergent in it, like, if your solution has extra, heavy molecules.
Yeah, put some tungsten molecules in for something. I don't know how but yes, you're right. If you made a heavy thing, then you would have a catenary,
Right, okay.
Uh-huh.
you see,
But you
hanging
could
there.
simulate-
We'll study those later on.
You could simulate a higher gravity just by putting a drag force on it.
Well, no, just hold it and go,
Exactly,
right? You get both the air pressure and the gravity making, and then
That's the
you have a
children.
vibration. That's a whole dynamics problem then. Yes, it's very interesting. And of course, the function becomes non-analytic in any of those cases.
Well, there's another interesting possibility. What if you have some sort of oscillation with this type of your film with this sort of weird boundary?
Well, this is going to have modes,
Yeah,
right?
probably.
And
Yeah.
if they're not too degenerate, you might be able to pick them by that oscillation frequency.
Oh,
Yeah. We'll talk a little bit about that in Unit 4. But yes, those are all interesting possibilities for generalizing what is already a beautiful thing, certainly the starting point with 0 curvature. Now, I'm going to go ahead and let you experiment with looking at these things using cross-eye, because that will help for some of our multiple functions that we have to look at here. So when you do that, you get both of them there. Now what I can do is I can zoom in to make it a little bigger, and then I can grab any one of these and turn them, and they'll turn together. So what you can do is, you stand back or sit where you're sitting, and I'll go ahead and do it myself so that I can tell you what it is that you do. Wherever you are, and you're right here, you put your finger up in front of you, turn your head so that the finger, 2 fingers that you're sort of looking at the screen, but they're 2 fingers for the price of 1, and you bring those fingers back until each one is touching the origin of its image. The right ghost finger is touching the right origin, and the left one is touching the left. And then you look at your finger. And then don't move anything. Try to look past your finger at the screen. And if you need glasses like I do, you put those glasses on so that the finger becomes blurred, and the image will be a perfect 3D, beautiful saddle coming out of the screen, sort of halfway in and halfway out of the screen. So this is the way you can look at 3D pictures without anything except your own finger to help you get your eyes to do what they don't naturally do, and that is decouple. And we've got plenty of time for this, since we don't have to finish all of the non-analytic stuff that comes at the end of this lecture. Are you able to get anything? It takes a little bit of practice, but
One other trick you might employ is for the notes. If you have a snapshot of the notes, you can play with the zoom Try zooming it, and then you might get the sweet spot where it
Yeah.
where you resolve it.
With the textbook or the notes, simply take the image and put it right up to your face so one eye is over the right image and the left eye is over the left image, and then just try to keep your eyes oriented that way as you pull away, and the trick will be to focus, but without letting your eyes go back to the normal angle that would be associated with putting a single image in focus. So yeah, it's worth trying this to get the Any luck?
Yeah, I got it.
Yeah.
Good. I have to retrain my eyes every time,
Yeah.
personally, and I've been at it for a while.
Yeah, it's one of those things. I can do it without the finger, but I've been practicing for so long that certainly if it's a really big image
So
and quite a
without-
distance apart, I use the finger then. But
So without finger, how do you do?
pardon?
Without using finger, how do you do this?
He makes his eyes look up.
TC, there are a couple of glasses back there. You can borrow those anytime you want. One of them is from the U.S. Marine Corps. It's used for looking at maps. The one that we sell from Edmunds, that's what you would, that one actually is broken, so it may not work. But you just put it on the table over the 3D image. Like this is the cardboard one that we sell at Edmunds for our funny drawings. And it's just got two lenses there, and they're just the right height for most people to focus and get it's the old-fashioned 1800 stereo Opticon.
Put your image that you're viewing.
And that's what that is, except it has magnification and all sorts of
Send it over a
extras
book.
to make it work.
Or
So
a piece of-
that's the most common way to do it, and it's pretty hard to use it up here because it's not. It's focused on that distance.
Right
The
there.
focal
If
distance
you
is just
flip
from
it
here.
and use this, like so.
And you look at a stereo image from the notes or whatever, or you hold it up to the screen. Up to the screen for the thing. Yeah.
Here's the
You-
higher quality one.
You would have screen right here like this one. It's all set up. Just put it down on it.
Is it working like a hologram?
Like a what?
In hologram,
Well, hologram does it in a massive way. It's actually creating a wavefront that looks like that thing from all angles. If you do this one and you move your head back and forth, it will twist, so it's always following you. The hologram doesn't follow you. It looks like it's really there. Yeah, that's a whole nother story.
What you're doing is
Someday we'll be
coercing
doing
one.
all of this stuff with holograms instead of this much better. We just have it right here in the room, and I can grab pieces of it. That will happen someday. Yeah.
You're basically coercing one eye to see one image. And that's the way the 3D TVs work too, by the various methods, passive and active.
Yeah. Okay, continuing. Just to look again at both the Jacobian, that's partial, the Cartesian with respect to these queer coordinates, which are the scalar and vector functions, gives you a Jacobian is quite unlike the one we had before with polar coordinates. And Jacobian is the inverse of that, or if it's the Q ones that you already know, obviously this is the one to calculate. You've got the Cartesian coordinates now in the denominator, and they're very convenient functions of x and y. So this is a case where the Jacobian is the first one you want to calculate, and then you take the inverse of that to get the Jacobian. Okay? And then the rows of the Jacobian, they give you what we might call the bra vectors, the contravariant vectors. Big E for uppercase phi, the vector potential, and big E for the uppercase A, which is the vector potential. Okay, so there are the actual vectors for that. Those are the contravariant vectors. The covariant vectors are the columns of the Jacobian, and as you we had when we did the polar coordinates. Okay, and they're similar, linear in x and y, with a minus sign here and there. Okay, now you put these two together. That is, make the dot product of phi with phi, phi with a with phi of course would be equal, and then a with a, and you'll discover the off diagonals are 0. Okay, and the reason for that, of course, is Riemann quotient. Okay, these make the coordinates orthogonal. There's the gradient of phi, that's the force vector there. There's the curl of the vector potential, that's also the force, remember, that's the half and half. So these half and half results assure that the dot product of phi with a, and you see I'm replacing them according to the Riemann relations, will automatically be 0 everywhere this thing is an analytic function. And then I've already said this, the divergence requirement, or Riemann-Cauchy requirement, demands that this second derivative sum be 0. And that's true for both the scalar potential and the vector potential. They both are Laplace solutions, Laplace equation solutions. Okay, so this more or less completes the geometry of any function that any analytic function that you think of will have something that obeys all the rules that we've just given here. So let's look at some others. I want to look at a monopole function. We've looked at z, why not 1 over z? Okay? And then we'll look at some powers. I think we'll have time for 1 over z squared, 1 over z cubed. Maybe we time for z squared as well. But I want to get through at least to see how these things relate to each other. Okay, and again we need stereo projection visualization to pull this off. Okay, so what we're going to do, this is another answer to what good are complex exponentials. Complex integrals define monopole fields and potentials, and that's what you use to build all of the others. So the monopole is a particularly weird one. Of all the power law fields, one lacks a power law potential. Now you'd say, what do you mean? A z to the n, I integrate that thing, I get z to the n plus 1 over n plus 1. What could go wrong? Well, what could go wrong is that n might come to minus 1, which is what we're talking about right now. You've got a problem. Now, one of the ways to get around this confinement like this was say, okay, I'm not going to use minus 1, I'm going to use minus 0.999999. Or plus 1 minus 1.00001. Then you can use this. Sort of. All right? But that's not what we came here to talk about. We want to really talk about the integral of 1 over z, which is a logarithm. Okay? So, if we're going to have a source force that looks like that, that will be the field of a monopole, two-dimensional field, monopole. Okay? It has a logarithmic potential, the integral of 1 over z. Okay, now that's an integral of x plus iy. That causes a little bit of problems. You deal with such a thing. Okay? How do I find the scalar potential? How do I break this thing into a real and imaginary part? And that's, of course, where the complex exponential saves you, because you already can write that thing in polar coordinates. Just write z as re to the I theta, and pull that apart. You have a logarithm of r, and you have a logarithm of an exponential, and the exponent is what comes out of that. So you'll have a scalar potential that looks like a logarithm of radius. That means that you'll have circular equipotential lines, but it'll get very weird right at the origin. It'll either be very deep, or if it's a minus sign, it'll be very much out of the screen. So that's what we're going to plot first. And then this one is really interesting. So this is the one function that really does some weird stuff. And that makes monopoles weird. Now, I'm going to go ahead and dismiss this particular fellow. And when I do that on this program, when I say I want to go over here and look at the monopole at origin is what it's called. As soon as I click this, the computer should say, hey, do you want to keep all those equipotentials that you made? You might want to keep them, but not in this case. Okay? So I'm just going to go here and say, OK, erase, and make whatever changes I'm going to have here. So the first thing that we'll do here is just go ahead and plot this logarithm real part here, okay? But also what we're looking at, of course, are the real and imaginary parts of this phi z. Now, what's really quite surprising is this function has the vectors all pointing away from origin. But they're pointing away and getting smaller by just the right amount, so there is no divergence anywhere in this field except right there where it's infinite. So that's kind of neat right there, just the fact that you can have a field like that with no divergence most places. But it's got a singularity, a real infinite singularity right there. Okay, now what I can do with this, of course, is plot streamlines. Now, the streamlines are particularly easy. I remember I had the thing checked for that. But this is going to be a very nice coordinate system that we have already worked with. It's called the polar coordinate system in 2D. Okay, and this is the radial part. So I'm asking the computer to remember a few of these lines, not being too careful to space them out very well. But, and that's really a bad one there. I should be more careful. But the idea is to make a fairly nice coordinate system out of the radial part, and then we'll come and hit the angular part. Okay, I think I need to fill up a little bit in here so that we can easily see this thing. Good enough, and then I go ahead and stop. It'll remember those, but now I'm going to plot the scalar. Okay, now I'm doing a very uneven job of that, but let's just start right about here. Circle. You even have a circle inside that. Another one here. You can see by the voltage that I'm really not making this thing equal spaced, but the computer is dutifully finding the normals to everything that this surface and radial line, normals to the radial lines of this surface. Okay, so up and up we come. The voltage is getting more and more positive, and it becomes negative as soon as I go below 1. You see, as soon as I go below 1, I have negative phi, and there's no limit to how negative I can get. You know, this is headed for infinity, but logarithmically, which means slowly. Okay, now with that, we can go ahead and look at the plot of the real part. That is the scalar potential. Okay, I might want to zoom in by 2. I think you can see what we've got here. I can turn it a little bit to make it a little more obvious. And this is something I guess I didn't point out before, is if I turn the thing right up so that it's almost level with us, then you should see that the equipotentials are just circles of a certain altitude. And the 3D isn't absolutely necessary to see what we're talking about here, but you could, still enjoy the behavior of the thing. Once you get it locked in, even if I move it, you should be able to hold it if I don't move too much. So we have this beautiful morning glory, sort of a trumpet flower that is describing the scalar potential. Okay? And there's the logarithmic curve, and it just keeps going up. It doesn't reach a plane very near here, but if we go way, 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 way out there, you'll have something that's pretty level. Okay? Now, using the same data that has been calculated from our choice, I go to the main control here and say, I'd like to plot the vector potential. And now you get something that's very different from what you just saw. The vector potential, and I'm going to try to swivel this thing around so it's obvious what we have here. I think you can already see the nature of this very bizarre thing. I think that will probably show it most clearly. What we have is a spiral staircase. Now the vector potential lines, which are the flow lines, right, before, now they're the crossbars. The flow is the red lines now. It's sort of blood flowing down the stairs on Halloween, which we're approaching here. Okay? And one thing that you can do with this is go back and get rid of the XY grid, the green stuff in the middle, and just show the A5 lines in the graph. So let's come back to that original graph. And there, I think, is a little clearer view of the streamlines now, which used to be equipotential lines, flowing downhill. And those are the stair states for stairs in a lighthouse, right? The stairs in a spiral arrangement. And that is, this is a case where the real part and the imaginary part of the force function are very different graphs. Okay? And very different integrals. And that's the thing that really comes out of this, is coming back here now to this. This is where last week's lecture would have ended if we didn't have a blowout of our power line.
Is it telling that the logarithm function is a multi-valued function, right?
No, that's a misconception that often comes up from the way they describe it. The logarithm function is very continuous except at this point. The thing that's going crazy here is this one. This one, as you go up in polar angle, just keeps screwing up. You see, I go 0 and then 2 pi. Well, I'm going to be 2 pi higher. I go another 2 pi and I'm that much higher again. So that's the one that's multi-valued, are the stairs.
Okay.
Right?
And is this stair...
And you can see that this would go forever as a helicoid. That's the name of the surface that you're looking there. It's called a helicoid. And it is a minimal surface. It's really a beautiful one. And we'll talk a little bit about that later on for other reasons, but that's definitely a thing. Now, one of the things we like to do is say, hey, let's do I times z. Not 1 over z, but I over z. Then you just flip these things. Now, you see those staircases have become the equipotentials. Now they're single valued. The logarithm, you see, now goes with the vector potential. So the vector potential will, and it'll simply reverse the colors on a graph like that. blue becomes red, red becomes blue, as you can see, is all that's happened between these two. This is a vortex. Very important, type of thing that we're going to play a little bit with in mechanics. Okay? The shape of a whirlpool, or the shape of the outside of some of the very perfect tornadoes you see marching across the Midwest at various times of the year. Okay, so these are two quite different things. All we've done is replace the real and imaginary parts with the other choice. Okay. Now, the integral, this is where the multivaluedness comes up. Since this is doing this, that is, this is just marching up forever and ever and ever, okay? Any path that goes n times around the origin at a constant r is going to tack onto itself n value of 2 pi I, and whatever constant I had. A, of course, will scale that. So there is the delta phi, the integral between phi equals 0 and 2 pi n of this function, 1 over z, okay, becoming that, which is exactly what I said there just a minute ago. The idea that the staircase goes forever is very, very much part of this thing. No other power law potential is going to have this pathology. It's only the one that goes crazy for n plus 1 with n equal minus 1. All of the others are capable of avoiding this kind of singularity. So here's a picture of the, these are 3D pictures that you can look at when you look at the lectures on the screen and see them in 3D, the normal way 3D is done, stereoscopically. So each turn adds a little bit. And this is a vortex. The vortex is just the opposite. Its A function is the logarithm, not multivalued. Its phi function now, as you go around the whirlpool, you keep gaining a potential energy, essentially, with this thing. If you were an actual force and were constrained to go on a circle, this thing would drive you faster and faster and faster and faster, you see. And you'd be getting a constant angular force all the time. And this is the one I'd like you to do for problem, and this is something that became useful to our galaxy group. I pointed out to Daniel Kennefic that the f of z equal some complex number over z, and you can pick your choice of what you want for that. It will take care of cataloging galaxies that have very well identified spiral arms, which is a huge number, as they're finding out. And these are all apparently corralled or being corralled by a huge, monstrous black hole, bigger than the one that's in our galaxy even, and we have a pretty good sized one, as it turns out. So you can make these things tighter and tighter, or looser and looser, depending on how you judge the what's the slope relative to some radius vector. Okay. Now let's go on. We have enough time here, I think, just to do a little bit of multiple analysis. And what I'm pointing out here, start with, this is where you take a complex derivative of an n pole and you get an n plus 1 pole, basically, but it's not quite that simple. Here we have a monopole field and its monopole potential. It's that crazy logarithm that you have to have if you're going to be working with f equal 1 over z. Now you let two line sources of equal but opposite force constants. That is, you put you make a copy of one, and then you put next to it a copy that's turned over. and that's what has been done here. Okay? So this is what you might call a physical dipole, because these are easy to make. What we're going to do is talk about the calculus dipole, I should suppose, where delta goes very smaller and smaller, approaches zero. But with a finite delta, such as is shown here, basically it's pretty simple. Here's the morning glory, but it has a nice sort of pretty steep slope, climbing up out of the hole and going up the tower here. So you go from minus infinity to plus infinity over a finite interval. But what happens if you close that interval, you see? That's like taking a derivative. You're doing f of z minus f of z plus delta z. Okay, and then divided by presumably delta z if you want to get the actual derivative, right? So that is what's coming next, you see. This is the derivative as delta approaches zero. Okay, that would probably be a more symmetric way to write it. And that's kind of what we're going to use here to make the dipole function. But once you look at it that way, and that's the next thing here, this is a two-pole, a dipole, an actual point dipole field, obtained by taking just the z derivative of the phi that goes with the monopole. Okay? So what you're ending up here is the derivative with respect to c of the logarithm. Okay? Well, that's 1 over z. So now you have a potential that's 1 over z. Okay? And a force field that's 1 minus something over z squared. Okay? And it looks like this. And the two isn't too different from the one over there, except that the slope from minus infinity to plus infinity is itself infinite. That's a straight line right up there. And then everything loops around those two functions. And this is a very neat sort of potential. You can go ahead and work out what it looks like. It has a very simple function in terms of polar coordinates, but it's not so bad in Cartesian either. So there's the scalar part, there's the vector part. Except for a change of x to minus y, they're the same. Except for a change of cosine to a minus sine, they're the same, the real and imaginary part. There's no big difference like there is for the monopole. And here's what it looks like when you look down on it. So presumably, if this is the equipotentials that go higher, 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 I should say lower, lower, but they go down and then jump back up again. And then these are the streamlines, and that's the thing that we can look at in 3D. And perhaps we'll wait till after the class to do that, and then you can take your time. But this is where 3D really helps to see who's up and who's down on that graph there. And these are streamlines that are going from a very high region to a very low region. They start out high and they loop around and go to low. That's what I want you to look for. But just the curves themselves, viewed in XY, this Thales rectangle again. There's a radius to the circle there, and this has to be a right angle, you see. So the R, you see, has to be the phi value, which is the size of the circle, times cosine theta. There's a hypotenuse, there's a projection onto the radius. Same sort of Thales construction that is involved in that crazy mechanics problem involving the optimum travel inside the Earth. Okay. So these are some things that are worth looking at. I'm just going to quit here with the next one. The next derivative up is quadrupole. So it goes up, 0th power of 2 is 1. 1st power of 2 is dipole. Okay? Then the next thing you do is the third power, okay? Let's see, what am I saying here? I have 0th power, 1 power, and I have second power, okay, that's the 4, that's this. And each time what you've done is you've taken something, made a copy of it, changed its sign, and then put it real close, but not on top of the other one. If you put it on top of it, you cancel it, because you made a copy, right? And then you'll put a minus sign on it. So you go up exponentially, and the next after this is octupole, and so forth. Now the thing that I want you maybe someday to study is how all of these, any function of z can be written as a linear combination of these things. Not just the positive power ones, but also negative. This is a multiple expansion. It's really a useful thing in 3 dimensions. There's a generalization of this, which is not trivial, but it's not that hard either. Once you understand this one, it makes it a lot easier. And what's, I think, really fun, and I'm just going to rush through this at this point here, as we go to the hexadecapole from the octupole. These are things that have their singularity at infinity. This is positive powers of C. Then there's this dipole and the monopole, 0 and 1 power. And then we have the minus 1 powers, and those correspond to dipoles at origin, quadrupole at origin. That's what we've been looking at just in the last few slides. So we look at a constant force field, and we looked at the AZ force field. You see, it was quadrupole at infinity. We didn't get around to z squared, but it's an octupole at infinity. And now we've looked at a dipole and quadrupole at the origin. Okay, so when you take this and make a scalar potential out of it, every one of them is a power law except this one that I've colored in red. Well, a thing that begs question here is, what would happen if I worked with a complex variable 1 over z, which is w? What if I took a unit circle and turned all the physicists that worry about nano things and made them worry about giga things, and all the astrophysicists that worry about giga things and made them look at nano things? That's 1 over z. That's a mapping 1 over z. Really an important mapping. 1 over z is an important function just because of this, but it's also one that lets you make a correspondence between having singularities at infinity and singularities up at the origin. And the way you get around that was by another Thales construction, which takes you from the z plane to the 1 over w plane. 1 over z plane, that's the w plane. Okay? And it's just, once again, a Thales rectangle, very easy to figure out what all the components of these things are and to analyze this. So you can see that if I have a monopole field at the north pole of this sphere that I'm using to project, then I'm going to have a negative monopole at the south pole. Okay, and you can see that in these in this connection. Okay, the other one that we had a quadrupole. I'm sorry, a dipole centered at the north pole. That corresponds to a constant field at the south pole. A quadrupole centered at the north pole makes the field that we talked about, the w squared in this case, and we were looking at z squared for the potential. That was f equal to a constant times the complex variable w. It'll be a quadratic field in the south pole. So this is a way to connect all of the different multipoles in a very beautiful way. Well, I think we're going to stop this. The rest of this is stuff that has to do with making the series, using the integrals, and Cauchy's theory of those integrals. And then the rest of this is after the mapping. There's a discussion of mapping here, which is another thing you can do with this stuff that's really interesting. And you can, a little bit of this is in the problems. But also you can do things that have sources, that have curls and divergence that are independent of each other. And a typical field looks like this. And it has rules that are very similar to mechanics. You have a derivative of position that gives you velocity, and a derivative of velocity gives you acceleration. And then you can make a connection just with a differential equation to that. But this has the same sort of thing. You have a source, it's like the acceleration. The integral of the source, the integral of the acceleration is velocity, the integral of the source is a vector field, and then the integral of the vector field is the potential. And then you have what's Poisson's equation, is equivalent to Newton's equation. So there's a connection between field theory, classical field theory, and classical mechanics that you would be worried here. This is what happens if you took the field that we had that had the hyperbolas. It makes this. And totally interesting in a sense, but also very complicated because all the coordinates for this one are very GCC. Okay, I think that we'll wind this up, and we'll be starting Unit 2 after this next week.